Today we'll talk about some data visualization techniques. Now this is the class BIOL476, 2025, and the class is called Analysis of Genetic Data. And this is lecture. So this material corresponds to lecture number 4. It's what we did last Wednesday in the class. So data visualization techniques. So by this we mean some visualization techniques in R used to somehow visualize our data. So usually our data are many numbers. Some visualization techniques try to depict all these numbers, so all data, and some other techniques try to compress the data and visualize just a compression of them, a summary of them. So a summary of the data. Okay. Now in our hypothetical example, imagine that we have some data in a matrix form as follows. So let's suppose that we measure some features. This could be, for example, the expression level of several genes. In this case, every gene is a feature. Or it can be things like weight, height, length of hair, color of the eye, and so on and so forth. So these are things that we measure for each one of our samples. So the samples are here on the columns. And then we might have individual 1, individual 2, and so on. And here we have feature 1, feature 2, and so on. So in the examples that we mainly use during the semester, features are genes, individuals are persons, and here we measure the expression level of gene 1 for individual 1, and so on. Okay, now if we have n features and m individuals, this matrix contains n by m values. So in our hypothetical example, these values, let's call them expression values, they will come, so they follow, that's how we write it, let's say a normal distribution with mean 100 and variance 10. This means the following. If we imagine the normal distribution like that, this will be 100 here. How wide is the distribution is instructed by the standard the variance here, the standard deviation. So this is a standard deviation actually, not the variance. And this is the mean of the distribution. Okay. And if we want to construct a table from this distribution, we just ask R to give us, for example, a value from this distribution. With some probability, the value will be chosen along this line. So this is the line of the expression levels, it's the x-axis, but the probability to choose a value here, for example, nearby the mean, is different and is larger than choosing a value away from the mean. This is illustrated here from the fact that the density plot of the distribution is higher around the mean than far away the mean. Okay, so we use R to get n by m values, and we put them in a matrix like that. We can do it immediately in R. So we open RStudio. We clean, or we make a new R script. We clean our memory here. And we are ready to start. So we say, okay, we want a matrix. Let's call it M equals matrix. And we need some values from a normal distribution. Our norm, let's say that we need to make a matrix with 100 rows and 10 columns, and let's say here if we have 100 rows and 10 columns, then we will have of course 1000 values, and the mean will be 100 and the standard deviation will be 10. Okay, this will be M. And now we need to visualize M. So if we just print it here, we will see all these values at the bottom panel of RStudio. However, our mind is not very capable of understanding all these values. If there is a variation, for example, in some column compared to some other column. Therefore, a very nice way to visualize this information is to do the following. We'll make a square plot like that will have exactly the same dimensions as our initial data, so as this data here, and so on. And now each value from here, let's say we have values that are 90 something and some other values here that are 110, and let's say that this is the minimum and this is the maximum. So all this range here from 90 to 110 will be split in different colors. For example, this one will be red and this one will be white, and every other value within this range will be a color between these two colors. So we start from red and then we go to yellow, then the yellow becomes more open yellow, and then we go eventually to white. So if we see a value that is red here, it means that the respective value here, which is the third value, this one, is a small value compared to the rest, of course. If a value here is white, like this one, then it means that the respective value here, which is somewhere here, will be a large value. Okay, so let's try to do this in the RStudio. This plot here is called the heatmap. In order to use the function heatmap, the function actually is called heatmap.to. In order to use this function, we need to load the library gplots. Okay, I load it, and now the heatmap. The heatmap gets the following arguments. We can even get the help of heatmap to here. It's an enhanced heat map. So it gets several arguments actually. So the first argument, as we see here, is this X, and the X is the data matrix that we want to plot. So here I use the matrix M. And then we have the call V, the distance function, the clustering function, the dendrogram function, and so on. So let's start with the easiest arguments. The first thing is that we don't want the dendrogram. So I will use here dendrogram equals false, or equals actually none, I guess. Yeah, none. And then call V equals false and row V equals false. I will explain this a bit later. And then I use scale equals none. I will also explain this a bit later. And also I'm looking for an argument called trace, and trace will be none as well. Okay, I will explain these arguments a bit later, but for the moment let's make the plot. Okay, if you see such a message like this one, it means that the space that you have here is a bit too small to fit this image that you want to create. The easiest solution is to make the space a bit larger. If this will not work, then the best idea is to save this figure in a PDF. Okay, still it will not work. Maybe I will zoom out everything. Okay, now it fits. So here are the 10 columns that I have, and here are the 100 rows that I have, and this is actually the heat map. When we see a red value, it means that the respective value in the matrix is small, and when I see a white or light yellow color, it means that the respective value in the initial matrix is large, as we see here in the color key. Now this blue line here is the histogram of the values. In other words, how many values in this data exist that are so small. Let's say 70. How many values there are that are 75? You see they are a bit more. How many values there are that are around 80? There are even a bit more. Most of the values are around 100, and this is something that we expect actually, because our data come from a normal distribution with mean 100, this here, and the same applies on the right side of this distribution. So we go up to 130 here. Now this is a very fast way to visualize the data, because immediately we see, for example, that there are no individuals that behave differently from other individuals, or there are no genes that behave differently from other genes. It's like we see a quite noisy thing, quite noisy information here that doesn't seem to we cannot see any specific pattern here. Okay. So this is the heat map. Now let's see what will happen if we change this function here, and let's say that we modify the matrix M by the following. We say that the columns 2, 7 and 8, they don't come from a normal distribution with mean 100 and standard deviation 10, but they come from a normal distribution with mean 180 and standard deviation 10. How many values there should be in these three columns? Well, if every column has 100 values, these three columns will have 300 values. So we need 300 values here. Okay. Now we go again and apply our stuff. You see here that all these values became darker, so these are the values that we got initially from a distribution of mean 100, and these are the three columns that we replaced afterwards with a standard distribution, a normal distribution from with mean 180. Now you see that the values of the initial values became a bit more red because the range here changed. It was from 70 to 130 up to here, and now it went from 70 to 200 something. Since the value 200 something became white now, it means that the 130 that we had earlier became dark yellow or a bit more light red. That's why you see that these values became darker. Okay. And of course the distribution of the values changed because now we have several values around 100 and several values around 180. This is the 180. Okay. Now let's see the following. Here I will apply now, I will say that the dendrogram, I want a dendrogram on the column. It means that here it will try to cluster the data using hierarchical clustering to cluster the columns, so to put columns that have similar values together. Now visually we see that these three columns should be together because all of them have values around 180, and these columns should be together because all of them have values around 100. Okay, since we will allow for a dendrogram to be on the columns, we need to say to R that you are allowed to change the order of the columns, and we do that by saying that call v equals true. Okay, and this is the plot now. So the columns 2, 8 and 7 are together. They form a cluster using this hierarchical clustering method, and the rest of the columns form another cluster that we see here. And the order of the genes is the same as it was before. We can allow also for row v equals true, and this will change also the order of the genes, trying to make a hierarchical clustering here. Okay, and we need to say, of course, that dendrograms equals both to visualize the clustering. Here we change the order of the genes, according to which more similar genes are one next to the other, but we didn't say to visualize it as a hierarchical clustering, and we do that now. So here we have a clustering of genes, and here we have a clustering of individuals. The clustering of individuals is very, very clear. Okay. Now let's try to see what is the importance of this scale parameter. I will modify again the data, and I will say that the first gene, let's say, of the first row, which is the first gene, comes from a normal distribution. How many values there are in the first gene? There are 10 values. One value for each individual. So 10 values, and let's say that they come from a normal distribution with mean 400 and standard deviation 10. Which means that the first gene has much higher expression levels than the rest of the gene. Okay, let's make again the heat map. Or I can even put a bit higher value here. Let's put not 400 but 2000. Okay, now everything looks red. And everything looks red actually because there is one value somewhere here, this one. Here is gene 1. You see that separate actually from the rest, this gene 1 and everything else here. And this gene has very, very high expression level, but since it captures the space of only one row, we cannot even visualize it here. We cannot even see that. So there is a very thin row here that probably is completely white, or it's under here that we cannot see. Okay. Now the problem is that all this information, the variation of the rest of the genes is lost because all of them actually is represented by this red color. So because the range is so huge, from 100 or from 70 to 2000, all the values became red because this range here, the first bin, is let's say from 70 to something like 200. Since all our values were from 70 to 200, more or less, except the first gene, all of them became red. So a way to save this would be to say that, okay, I want to have a scaling on the rows or on the columns. We will see that now. So here is the situation. Clustering remained the same. However, now on every row, we have a scaling on this range. We have a scaling around 0, and so in principle we have a modification of the values to a z-score scale, which means that the mean will be 0 and the standard deviation will be 1 for each row. How we do that is that we get every value of the row and we divide it and we subtract from each value of the row its mean, the mean of the row, and we divide the value by the standard deviation. Which means that now some values will become negative, since there are smaller values than the mean, and some other values will become positive, since there are definitely some values that are higher than the mean. By dividing with the standard deviation, we get ensured that the standard deviation of the whole line will be 1. Okay, and you see now that the information is shown again. The clustering didn't change, so still gene 1 is very separate from everything else. But by normalizing the values on each row, we are able to visualize with the right colors the plot again. We can do the same by applying column scaling. Now this probably will not save us so much. Why? Because these values here are much higher. And let's say that we have a value 1000 here and all the values are about 100, which means that the mean value of this row will be, of this column will be something like, let's say, 100 or so. So this will be around 100, the mean. And then we divide by the standard deviation as well, but this value here will remain very high compared to the rest. So this value here for gene 1 will be again the white. Everything else now will be on the mean, so it will be around 0. And that's why this is again not informative. Since we have a large value on one row, then we need to scale by row, to scale every row independently from the rest, so that these values here will not interact with these values here. Okay. Now, if we would have one column that is very high, for some reason one patient values are very high, let's say that patient 1 now has these values, and here we need 100 actually, so I ran it from the beginning, everything. Now the row scaling will not help us exactly for the same reasons that previously the row scale the column scale didn't help. Now we need to do column scaling so that each column is independently scaled from every other one. And now we can see the differences on the data. Now, the first patient, which is this one, is clearly separated from everyone else. You see that here. The columns 2, 7, and 8 are also separated from everything else. But now, since we scaled on each column, we will not see them as different than the rest, because every column now became independent from the rest, which means that even though these three columns are having higher values in reality than these columns here, we cannot visualize it because we scale every column independently from any other column. And I guess we can scale also in both dimensions. No, this is not possible. It's none, row, or column. So be careful with scaling, because you don't see the actual values, you see an independent scaling values either on rows or on columns. And we do that just to be able to visualize values that range several orders of magnitude, like here, for example. Most of the values are around 100, but there is one column that has values around 2000. Okay, so this is the heat map. Oh, and the trace argument. Yeah, let me show this as well. So trace, if we leave it by default, then we'll see an ugly light blue values here, and this is actually the histogram or kind of bar plot of these values. So this is the mean of the column, and these values are higher than the mean, and these values here are lower than the mean, this higher than the mean, this lower than the mean, and so on and so forth, of each column independently. But I find that this is very annoying when we try to visualize data, so usually I use trace equals none, like that. Okay, so this was the heat map. In the next video, we will see how to visualize data using some clustering information, more or less like this one, So let's make a hierarchical clustering visualization. To do this, we need to apply the method hclust. But first, so let's say that we want to make a histogram. I will make it like, okay, let's remove this row here. And let's reconstruct the matrix. So now the matrix, all the columns come from a normal distribution with mean 100, except columns 2, 7, and 8, which come from a distribution with mean 180. What we will do is that we will calculate the distances between every pair of columns. And we do it like that. So we have the matrix here. And let's say that we want to calculate the distance between column I and column J. So we have 100 values here and 100 values here. Now an easy way to calculate the distance between these two vectors is the following. We get the value of column I, the first value, which is this one. We subtract it from the first value of column J. Now this difference will be very small if these two values are similar, and it will be large if these two values are different. Now if this value is smaller than this one, then it will be a negative number. If this value is larger than this one, it will be a positive number. Since we are interested in the distance, we would prefer to get the square of this function, of this operation here, which is always positive. With the same way, we calculate the difference between these two values. And again we have a positive value here. And like that we get all the distances. Then we sum them up. So if this vector is very different than this vector, this summation will be also large value. And finally, we get the square root of this. We get the square root because if, for example, these are some units, let's say, okay, here we cannot have kilos or meters or whatever, but let's say that we could have kilos. This is kilo, this is kilo. Now the difference will be kilo, but the square root will be kilos on the square. So if we want this measurement to be again with units kilos, it's better to get the square root of this. So that's why we get the square root of this number. Okay, so this is called actually the Euclidean distance. The Euclidean distance, we can calculate it very easily using the function dist in R. So dist m is kind of a matrix, but not exactly. It's called a triangular matrix, which shows only the distances between every pair. So this is the distance between the first column and the second column. This is the distance between the first column and the third column, and so on, up to 100. Sorry, up to, let's see what we have here. Okay, so my mistake. When we calculate the distance like this, it calculates the distances between every row pair of the matrix. So since the matrix is 100 rows by 10 columns, it will be 100 by 100, and it will actually show the distances between the rows, so the distances between the genes. But we don't want that. We want actually the distances between the columns. The problem is that the function dist calculates the distances always between rows. In order to calculate the distance between the columns, we need to shift, to switch this matrix so that the columns will become rows and the rows will become columns. And we achieve this by using the function t, which is the transpose function. So Tm compared to M is a matrix, again, which is 10 by 100. It has 10 rows and 100 columns, and the first row of Tm was actually the first column of M, and so on. And now dist will work. Okay, and since we did that, it's very easy to use the function hclast with this distance M inside there in order to make a hierarchical clustering of this data. You see, you got a dendrogram of these 10 vectors, 10 columns that we initially had. And of course the columns 2, 7 and 8 are together, and all the rest are forming another cluster. So for example here, we don't even see the values at all. We don't get any summary of the data, but we get some information. We get the information that we have two very different kinds of individuals. These individuals are very similar to each other. These individuals are very similar to each other, but between them there is a huge distance, illustrated here by these long branches. Okay, so what we have done here is that we have used the function hclast, which performs hierarchical clustering. It has several options, some methods to group things together. Here is a complete method. I will explain that in the class. Usually we use the average actually. So we can say here that method equals to average. It will be very similar, the result, as we had before. So this hclast returns an object that we can plot here, we can print here. It's just an object of R. It's the call of the hclast function, cluster method average, distance Euclidean, a number of objects 10. These are these 10 objects here. But this object returned by R can be easily plotted and make a tree-like structure using the function plot. And it's this one is a result. So this is a hierarchical clustering approach to visualize data. Remember that the histogram, the heatmap actually already could do this plot on the top of it. And so these are two methods that can be used to visualize complex matrices. And another method is the PCA. I will explain the math of it in a different lecture, but for the moment let's try it. We will use the function prcomp to do the math for us with the matrix M, scale, true, center equals true, and then plot PCA x1 and PCA x2. These are the... Okay, here again we need to transpose it because it does a PCA on the rows, we need it on the columns. And here is the result. We see that here we have three values. These are actually the 2, 7, and 8 columns, very, very distinct from the rest. Again, this plot looks like the hierarchical clustering plot, which clusters the group into two parts. In principle, PCA is doing something else. Its purpose is not to cluster the data, but actually to plot the data in other dimensions than the original, and fewer dimensions than the original usually, and this dimension represent the direction of the highest variances. So for example, along this dimension the variance of the initial data is the highest, and this is the reason that actually it manages to separate these three values from these three values. Since these values are very, very different than this one, automatically the dimension of the highest variance is this one. So here we see again a summary of the data, a very compressed form of the data, that we have three different values than on the rest. Again, the math and the details of the PCA will come in a later class. Okay, so these are three matrix visualization techniques, and in the next video we will see some vector visualization techniques. So that's for the moment.